Often, the sample data collected consists of drawing the same data from each member of the sample at two different points in time. Usually before something has occurred, an initial value, and then comparing it to a value that occurs later on. Most of the time, this involves generating a single sample from a single population and then applying a treatment to it to compare what happened before the treatment and what happened after, such as a person's weight at the beginning of a exercise or diet program, and then perhaps their weight a month later or 2 months later. The rule here is that the sample must be randomly selected. A typical requirement for all sample generation. Second, that the data must be taken from each member of the sample twice. Once is going to occur at the beginning or before a treatment is applied. And again after the treatment is applied. The idea is to compare and see if the treatment made a difference. In this way, we have pairs of data values for each member of the sample. So one of the things that matters here is that we have a single sample that is of a single size. When we tested the difference between means of independent samples, we had to contest with the fact that the samples may be different sizes, and very often were different sizes. And in turn, that made determining the degrees of freedom for our test more complicated. It also meant that finding the standard error, which is the denominator of the calculation of the test statistic, was considerably more complicated. We also had to contend with the possibility that the two populations, which were separate populations, had separate variances. And we had to deal with it's possible that those variances were the same or close enough to each other to be treated as if they were the same, or if it was completely unknown whether they were the same, or if they were different enough that we knew they were not the same. In this case, we don't have to worry about that because it is a single sample drawn from a single population. And that's going to make our degrees of freedom much easier to determine. It also is going to make the calculation of our test statistic considerably easier, or at least to have a considerably simpler appearing formula. The idea here is that for each data pair, we're going to take the difference between the data value before treatment and the data value after treatment. Now, this may produce a positive difference if the value has gone down, if the value of the sample data has decreased. It may produce a negative difference if the data value has increased. The idea then is that in order to determine whether the whether there is an actual difference, whether the application of this treatment has produced a noticeable effect, we need to do this difference for each data value, and then we need the mean of the differences. This would be d bar, and of course that would come from adding up all of the differences and dividing by n, where n, of course, is the sample size, as it usually is. The idea, then, is that the sampling distribution for d bar will be a t-distribution with n minus 1 degrees of freedom. We don't have any complicated formulas for degrees of freedom. We don't have even the conservative method of choosing the smaller of the two samples and subtracting one from it, because this is a single sample. So the degrees of freedom is quite easy to deal with. It is simply n minus 1. The idea then, of course, is that the test statistic is going to be a t-value, and it's going to come from the sample mean difference minus the claimed mean difference of the population over the standard deviation of the population of the differences. Now, of course, since we don't have the population standard deviation, we are not using a z-test. We're using a t-test because we have the sample standard deviation of the differences. And that is, of course, divided by the square root of the sample size. This means that not only are we going to have to calculate the difference for each pair of data, and then the mean difference for each pair of data, we are also going to have to calculate the standard deviation of the differences. That is going to come from the formula, the square root of the sum of the squared deviations of the differences between the pairs of values over n minus 1. Now, of course, we can do it that way, but there is an alternative formula that often works better for us. It is the square root of the sum of the squared differences minus the sum of the differences, which is then squared, over n, all over n minus 1. Since we're going to have to be calculating the difference for each pair, it from there is actually fairly easy to also square each difference and then add those up, as we'll see in the following example. In this example, a golf club manufacturer claims that golfers can lower their scores by using the manufacturer's newly designed golf clubs. To test this, 8 golfers are randomly selected, and each is asked to give their most recent score. Then they're given the new clubs, and they use those new clubs for a month. This is what we would refer to as the treatment. They are given something that is expected to produce a change. And then we see if that change occurs. So after using the new clubs for 1 month, we again go back and ask those same golfers, now what's your most recent score? Those scores are shown in the table, and we're going to assume the golf scores are normally distributed, which is a standard assumption to make. The question then, is there enough evidence to support the manufacturer's claim? And we will be using a 0.10 significance level. So what we can see here is that the first golfer was scoring an 89, and after using the new clubs, scored an 83. So their score went down by 6. That is going to be the difference. 89 minus 83 is a difference of 6. The second golfer had scored 84 with the old clubs, and with the new clubs scored 83. That difference is 1. The third golfer went from a 96 to a 92. That's a difference of 4. The fourth golfer, their score actually went from 82 up to an 84, so their difference is -2, and so on down the line. The idea then is, in order to find the average distance, or the average difference rather, we need to add all of these up and divide by the sample size. In this case, if we add these, we get a sum of 13. So our mean difference is going to be 13 over 8, which fortunately for us turns into a very nice decimal. Nothing that requires any rounding. Now we also need the standard deviation of the differences. So again, we have our choice of formula that we're going to use. So we could either take the mean of the differences that we have, and we can find the deviation from it for each member of the sample, and then square those, and then add them up. But it is probably faster in this case to simply square the distances themselves. 6 squared is 36, 1 squared is 1, 4 squared is 16, -2 squared is +4, 5 squared is 25, and of course 0 squared is 0. Adding these up gives us a sum of 87. So to calculate our standard deviation, we can take the sum of the squared differences minus the sum of the differences themselves, which then gets squared, over n, and then divide that all by n minus 1, which would give us 87 minus 13 squared over 8, all over 8 minus 1. Throwing all of this into our calculator will give us a value of 3.0677 if we round it. Again, always best not to round if we can avoid it, or at least to use as many decimal places as we can get away with. So with these values in mind, we can now go about doing our hypothesis test. We start with the hypotheses themselves. The manufacturer claims that the scores would be lowered. So they expect that the mean of the differences should be greater than 0. Greater than 0 because what we see is that when the score went down, when we got a better score, we ended up with a positive difference. A positive difference represents that our score went down. So the manufacturer claims that the mean difference is positive, meaning the scores, on average, went down. The null hypothesis, then, of course, is the statement of equality. Now, whether we call it less than or equal to, or whether we call it just equal to, either way, it is meant to include the statement of equality upon which the hypothesis test is based. So our test statistic is going to come from our mean difference minus the claimed mean difference over the standard deviation of the differences over the square root of n. Our mean difference was 1.625. The claimed mean difference, as we see up here, is 0. Our standard deviation was our approximately 3.0677, and that is going to have to be divided by the square root of our sample size, 8. A quick calculation here should give us a t-value, a test statistic value, of approximately 1.498. Once again, we can use either the p-value or the critical value method. In this case, our alpha was 0.10, and our degrees of freedom is 1 less than the sample size. So our p-value is going to be the probability of having a t-score that is more extreme, further to the right, than the 1.498 test statistic that we have. This being a right tail test, we don't have to double the p-value. We can just take this probability straight out. And again, from our calculator, with a degrees of freedom of 7, we get a p-value of 0.0888, etc. And this is less than our alpha value of 0.10. This is going to give us the decision to reject H sub 0. So we are going to reject the hypothesis that there is no difference, which means we are believing the alternative hypothesis. We are believing the claim that the clubs have shown a difference in scores, that the scores have improved. So there is enough evidence to support the claim that the new clubs lower the scores. So once again, the test procedure is the same. The only difference, once again, is in the calculation of the test statistic, the formula that is used, and some of the methods. In this case, we have to calculate the mean of the differences and the standard deviation of the differences in order to calculate our test statistic. Now, in some cases, this may be given to you, but in most cases, you will see that you are given actually a table of values before and after, and that you will have to calculate the distances yourself. Depending on the size of the sample, it will very likely be advantageous to do this with a spreadsheet. So by all means, please use a spreadsheet to do this. If it's a small enough sample, and if the values are friendly enough, as they were in this problem, perhaps doing it by hand is not incredibly difficult, but certainly you may use a spreadsheet to do these for larger samples or for samples where the data values are not as nice as they were here.